So today I want us to discuss normal probability distribution. Normal probability distribution. Normal probability distribution is what now we need to look at. And that one, I want us to go to the question of May 2021. Or rather, maybe for a different one, so that that one I can. May 2014. May 2014. Question 2B. Check whether you are able to see that. Have you seen the question? Mohammed?
Yes.
You have seen the question?
No.
In the past papers? May 2014. Question 2B. Not yet.
Yes, Mr. Kimani.
Yes.
Sorry, I had some connection. What was your question?
Then, have you seen this question?
May 2014 question 2B.
Yes.
Yes, I have seen.
Good.
It is here.
So the question says that
The cost of
accountant of
Mutengo.
Jengo Construction Limited has established that the total cost of a certain project is normally distributed with a mean of 85,20,000 and a standard deviation of 1,700,000. The expected total revenue of the project is 10 million. So you are told to get the probability that the project will be profitable. Probability that should be profitable. So, probability of being profitable, Now, the first thing that we need to note is that the project is profitable. It is profitable if revenue is greater than costs. If revenue is greater than costs. So we will then be looking at the probability that revenue is greater than cost. So that will require we draw a diagram that looks like this. That is what we do with the normal. So here we write the mean, and here we write the standard deviation. So if our figures are in thousands, the mean is 8520, it's written here, and the standard deviation is 1,700,000. And the revenue, we are told it is 10 million. The revenue is 10. So this one is called X1, which is 10,000 here. So this project will be profitable as long as these costs are less than 10 million, so that the revenue will be bigger than the cost. So that means the area that we are interested in is the whole of this. The whole of this, that way. So we get Z1 as X1 minus X bar. You divide by standard deviation. So this will be 10,000 minus 8520. You divide by 1,700. So that value, we give it to 2 decimals. We give it 2 decimals, so it is 10,000 minus 8520 divided by 1,700. To 2 decimals, we get 0.87. 0.87. So once you have gotten that, you go to the normal tables. You go to the normal tables. There is a table that I sent you. Let me get to my copy now. One. So I sent you a copy like this. So this copy, or what you do, you read this side 0.8 here, and then you go to 7. So where 0.8 meets 7, it is 0.3078. So that now means probability that X is less than or equal to 10,000, it is 0.87 is 0.3078. Now, when you read from the tables, this one is always the probability between X bar and X1. So this is the probability between 85 and 10,000. But we also require this other side. So this other side is equal to 0.5. Because this side have 0.5, this other side 0.5. So you add 0.5 and the probability will be 0.8078. 0.8078. So that is how you get that. The next question says probability that the project will not be profitable. So probability of not being profitable. Of not being profitable. Probability of not being profitable. So this one, it will simply be 1 minus probability of being profitable. Of being profitable. And therefore, this will be 1 minus 0.8078. So if you take your calculator, it will help you to see 1 minus 0.8078 is 0.1922. Okay, then the amount of revenue that should be earned from the project in order to have 0.99% or 0.99 chance of the company making a profit. The required revenue. So the required revenue, you will argue like this. We want the normal distribution to look like that. This is X bar here, which is 8520. Standard deviation is 1700. Standard deviation is 1700. And now the probability of making profit here, the revenue here is what we do not know. The revenue is what we do not know. But we want the whole of this area. The whole of this area to be 0.99. To be 0.99. So if it is 0.99, what that means is that this region is 0.5 up to here, and then this one is 0.49. Because I've told you from here to the end, it is 0.5. And then if from here now to here, it is 99, then it means this one should be 49. So what we do, if you look at this formula here, this one here, we make x1 the subject. When you make x1 the subject, you will say that x1 is equal to x bar plus z standard deviation. Plus z standard deviation. So we already know that this is 8520. That is the mean. Plus z. Now z is obtained from the tables. So you get inside here the tables, you look for 0.49. You may not get it exactly. So if you don't get it exactly, you pick the figure that is either slightly above it or slightly below it. Slightly below or slightly above. So when I start looking for 0.49, I get this one, 0.4901, which is at 2.33. So that is 2.33. And one thing you should also notice very well is that when you are above the x bar, when your x is above the x bar, the value of Z is always positive. The value of Z is always positive. But when you're on the lower side, the value of Z is negative. So now I multiply by 1700. And when I multiply by 1700, I will say 2.33 times 1700 plus 8520 is 12,481,000. So this one now, I'm saying it is 12,481,000. So that is the revenue that should be earned in order to get that. So are we okay there? Are we okay?
Yes, madam.
I can't hear you.
Yes, we are good.
Good. Let us go to the question of May 2016, question 2B. The question of May 2016, question 2B. May 2016, sorry, May 2016, question 2B. Okay, so the question says, I hope you are there. The question says that the mean weight of 500 packaging tins from a production process are normally distributed with a mean weight of 151 grams and a standard deviation of 15 grams. Required, the number of packaging tins that weigh between 120 grams and 155 grams. So, between 120 and 155 grams. 120 grams and 155 grams. That is what you are told to look for. So as usual, I have told you, you begin by drawing the normal distribution curve that looks this way. So here we have the mean, that is X bar. X bar, we are told we have a mean of 151. And we have a standard deviation of 15. We have a standard deviation of 15. So 120 is somewhere here. So this is X1, 120. 155, we put it somewhere here and call it X2, 155. So you shade the area that you desire. So we are looking for the area between 120 and 155. That is what you are looking for. So with that now, you get Z1. Z1 is obtained as X1 minus X bar. You divide by standard deviation. So this will be 120 minus 151. You divide by 15. And then you look for Z2, which is given as X2 minus X bar. You divide by standard deviation. And this will be 155 minus 151. You divide by 15. And these values are always expressed in two decimals. So I'm going to have 120 minus 151 divided by 15. It is minus 2.07. 2.07 when you express to two decimals. And then 155 minus 151, you divide by 15. It is 0.27. Once again, when you express it in terms of two decimals. When you express it in terms of two decimals. So from the tables, probability that we are between 120 and 155 is equal to, so once again, as I have told you, you go to your table here. You first of all read this one, 2.07. And even if it's negative, we read it as positive. So 2.07. So 2.0 unaifuata up to where there is 7. 0.4808. That is 0.4808 plus 0.27. So you come and look for 0.2 up here. 0.27. It is 0.1. 0.1064. 0.1064. So if you take your calc and add those values, you say 0.4808 plus 0.104 is 0.5872. So the number of teams, if you are now told to tell us the number of teams, what you do, you take this probability 0.5872 multiplied by the total number of teams. The total number of teams in our question is 500. So you multiply by 500. So this times 500 gives me 293.6. Teams, 293.6 teams, which you can round down to 293 or even round up to 294. The number of packaging teams that weigh more than 185 grams. So we get now the ones that are more than 185 grams. So this one, you again draw something like this. That way. And we always begin with the mean is X bar 151. Standard deviation here is 15. So if you are told more than 185, you come here and mark X1 185 this way. So that is the area that we want greater than. So we then get Z1 as X1 minus X bar. We divide by standard deviation. And this becomes 185 minus 151. You divide by 15. So if you go to the calc, you will find 185 minus 151 divided by 15 as 2.27. 2.27. So the probability that X is greater than 185 or equal to. Now, as I told you earlier, anytime you have a value of Z and you read the values from the table, it gives you the probability from your mean to your X. So when we go to the table to read this one, what we shall get is the probability from here to here. But that is not what we want. We want this other side. So how we will get what we want is by saying we know that from here all the way to the end is 0.5. The whole of it is 0.5. So we now subtract this one that we don't want, which we are going to get from the tables. So you go to the tables and get 2.2 here, 2.2, then it will be all the way to where there is 7. And 2.27, I'm getting 0.48. 4884. So 0.5 minus 0.4884, 0.0116. So with that now, the number of teams will again be 0.0116 times 500 times 500, and you get 5.8, which you can again round down to 5 or round up to 6. Are we okay?
Mr. Balimu?
Yeah.
Why are we multiplying by the mean weight to get the total weight?
Why we are multiplying by 500 is to get the number of teams. Is that okay?
Yes.
Okay, good. Because we are told all the teams are 500. You see, this probability, the values of probabilities here, they are usually for 1 is 1. Probability is expressed in terms of 1. So this refers to 1. So if you are given a figure greater than 1 and you want to know the total, then you simply multiply by that figure.
Thank you so much.
Multiply by that figure. Is that okay?
Yes.
Good. So let me do another one so that we can be comfortable with that. Let's look for another one. Yeah, December 2017. December 2017, question 2C. Let's get there. So we have said the question of December 2017, question 2C. The question says, a survey conducted on citizens of certain countries to determine the annual per capita income indicated that the annual income of the citizens is normally distributed with a mean of shillings 980,000 and a standard deviation of 160,000. One citizen was selected at random from the country. You are required to get the probability that the annual income of the citizen is greater than 500,000. So greater than 500,000. So once again, we draw the Kasipu table. This is the mean here. And the mean, we are told it was 980,000. And the standard deviation, we are told it is 160,000. 160,000. So if it's greater than 500, so 500 must be on the lower side here. So this is X1, which is 500,000. And because we are looking for greater than, then we want the whole of this. We want the whole of that region. So again, we get our Z1 as X1 minus X bar. You divide by standard deviation. So this will be 500,000 minus 980,000. You divide by 160,000. So when you do so, this will be 500 minus 980 divided by 160 is minus 3.00. So the probability that X is greater than or equal to 500,000. So again, we go to the tables. And when we go to the table, we read 3. So 3.00 is here, 0.4987. 0.4987. And as I've been saying, this is the probability from your x bar to your x1. So it is the probability from 980 to 500. But you can see we also want even the higher side. So you say plus the other side, which is 0.5, and now your probability will be 0.9987. 9987. The next one is greater than 1220. You're told greater than 1220. Greater than 1220,000. So once again, you draw your normal curve like that. You tell us that the mean here is 980,000. X1 here is 1220,000. So we want this greater than. And the standard deviation here is 160. 160. So Z1 again will be X1 minus X bar divided by standard deviation. So this will be 1220,000 minus 980,000. You divide by 160. Divide by 160. So this becomes 1220 minus 980 divided by 160 is 1.50. So probability that X is greater than or equal to 1220,000. So as I have been saying, when you read from the tables, what you are going to get is the probability from this X bar is X1. But because we want the upper side, what we will need to do is to say 0.5 minus now what we shall read based on this 1.5. So we once again go to the table where we have 1.50 and get 0.4332. So 0.5 minus 0.4332 is 0.0668. 0.0668. And then the last one is between 852 and 1100. So between 852,000 and 1100 or 1.1 million. So this one is drawn again like this. We have X bar here, which is 980,000. Standard deviation here is 160,000. This is our X2, which is 1.1. This is our X1, which is 852,000. So you shade this because that is the area that we want. That is the area that we want. So now we get Z1 as 852,000 minus 980,000. You divide by 160,000. And then Z2 will be 1.1 million minus 980,000. You divide by 160,000. 160,000. So sasa hii itakuwa 852 minus 980 divide by 160 is minus 0.80. Then 1100 minus 980 divide by 160, 0.75. 0.75. So from the tables, probability that we are between 52,000 and 1.1 is equal to, so you go to the tables and read 0.8, it is 2881. 881. Now that 2881 is the probability from this x1 to this x bar. So we go now read for this one 0.75. 0.75. I'm getting 2734. So I say plus 0.2734. And in so doing, that would be 0.2881 plus 0.2734. 0.5615. 5615. So I think that is good enough for normal probability distribution. Is that okay?
Yes, Malim.
Good. Now for your own practice, maybe I look for one or two questions. You can attempt May 2021 question 1C. May 2021 question 1C. You can try that. It will be good. The last or the next thing I need to look at in this area of probabilities is called probability trees. So that we are through with this area. So I now want us to look at probability trees. Now, probability tree is simply a presentation of just a presentation of experiments together with their outcomes in form of a diagram. And from there, we are able to handle the probabilities. So I want to begin with the question of November 2016, question 1B. November 2016, question 1B. So the question says, the following information relates to product X, which is susceptible to 3 types of defects, A, B, and C. The probability of product X containing defect C depends on whether the product contains any other defects, A or B. The probabilities of the product containing the defects are as follows. So we are given that, and we are told to come up with those probabilities. So what you do is, first of all, to come up with a sketch. And what we are dealing with is an issue of defects. And defect, it is either you have a defect or you don't have a defect. And we have 3 types of defects in this question. That will be analyzed like this. It is either you have A or you don't have A. You have defect A or you don't have defect A. Then you have B or you don't have B. And then you have C or you don't have C. That is how it is done as a sketch. So what you can see, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 tails. So when you know how many tails you have, you now do a fair copy. And you estimate from your side, your page, where the tree will go up to. So if my tree will come up to here, I now come and do 8. 1, 2, 3, 4, 5, 6, 7. I'll need 8 here. So if there are 8 there, I must now do already this so that they fit. So that is how the tree is drawn. And we are saying you have A or you don't have A. When you don't have A, we write it apostrophe that way. Or you have B, don't have B, B here, you don't have B. Then there is C here, and you don't have C. C, you don't have C. C, you don't have. C, you don't have. So you see now, this is the fair copy, what we have gotten from the sketch. From there, we assign the probabilities as we have been told. We assign the probabilities. So the probabilities are, the probability of having defect A is 0.15. So 0.15. So not having is 0.85, because the two probabilities that come from the same point here must always add to 1. Must always add to 1. So this plus this should be 1. Then having B is 0.14. So this is 0.14. So this must be 0.86. 0.14 and 0.86. That way. Then from there we are told defect C if neither contains A or B. So when you don't have A and you don't have B, the probability that you will have C is 0.3 here. So this not C is 0.7. That way. And if you contain A or B, so A or B means these others. But there is another point that we need to consider before we capture all of them, that C, if it contains both A and B. So if you contain both A and B here, the probability of having C is 0.1. So not C then must be 0.9. Must be 0.9 there. And therefore, this 0.2 is what remains for the others. So here you put 0.2, 0.8, 0.2, and 0.8 that way. So when now you are told to get the probability that you contain contains no defects. So probability that they contains no defects. contains no defect, it simply means the probability that you don't have A, you don't have B, and you don't have C. That's the meaning. You don't have A, you don't have B, and you don't have C. When they are connected by the word add, it means you multiply. So not having A is 0.85. Not having B is 0.86. And not having C is 0.7. So if you seek help from the calc, you'll be able to say 0.85 times 0.86 times 0.7, and you tell us it is 0.5117. 0.5117. The next one is contains only one. So contains only one defect. Only one defect. So if you contain only one defect, there are three possibilities. Either you have A, but you don't have B, and you don't have C. You don't have C. Or you don't have A, you have B, and you don't have C. Or probability that you don't have A, you also don't have B, but you have C. So that is the meaning of one defect. So we start following these ones in the tree here. So A is 0.15 times not B 0.86 times not C 0.8. When you have the word all, it becomes plus. It becomes plus. So plus A naught 0.85 multiplied B 0.14 multiplied by C naught 0.8 plus A naught, that is 0.85 times B naught 0.86 times C 0.3. So if you put those figures in the calc, you will get 0.15 times 0.86 times 0.8 plus 0.85 times 0.14 times 0.8 plus 0.85 times 0.86 times 0.3, and I'm getting 0.4177. So that is how you handle a probability tree. Are we okay now at that point?
Yes.
Good. So I can do one more. You as a probability we are done. And that is the question of September 2015. question 5A. September 2015, question 5A. So the question says that a machine is composed of 3 components, X, Y, and Z. The probability that component X is in good working condition is 7 out of 10. If component X is in good working condition, the probability that component Y is in good working condition is 3 out of 5. If component X is in good working condition, the probability that component Y is in good working condition is a third. If components X and Y are in good working condition, the probability that component Z is in good working condition is 5 out of 6. Otherwise, it is 1 out of 10. The machine can only be effective when component Z is in good working condition. So you are told to get the probability that the machine is effective. So again, in this case, it is the issue of the machine being effective. And as we have said, you start by the sketch. The machine has 3 components. So component 1 is either effective or not effective. Component 2, the same thing. And component 3, the same thing, either effective or not effective. That is the sketch. Now, looking at that sketch, you will see it is exactly like this one that we had. It is exactly like this one. So we will draw a tree that is similar to this. We will draw a tree. But for me, what I will do, I will just grab here. So it is either X is working or X is not working, Y is working or Y is not working, Y is working or Y is not working. Then Z is working or Z is not working, Z working, Z not working, Z working, Z not, Z working, and Z not. So now, the question says the probability that X is working is 7 out of 10. So this is 7 out of 10, and not working then is 3 out of 10. 3 out of 10, so that we get to 1. the probability that component, rather, if X is in good working condition, if X is working.
Malimu.
Yes.
Malimu.
Yes, I can hear you.
Yeah, I prefer we use decimals 0.7, 0.3. I think that is better for even space purposes.
Okay, we can still convert it to decimals. So if we convert
I believe
decimals,
that is better if it is possible.
This will be 0.7 and 0.3. Is that okay?
Yes.
Good. So then when we got Y, or rather we are told, if component X is in good working condition, the probability that Y is in good working condition is 3 out of 5. So get 3 divided by 5 is 0.6. So Y working here is 0.6. So not working is 0.4. 0.6 and 0.4. Higher. If X is not in good working condition, the probability that Y is in good working condition is a third. 1 divided by 3 is 0.3. So we can take 0.3 here, so that this becomes 0.7. 0.3, that becomes 0.7. Higher. If component X and Y are in good working condition, X is working, Y is working, the probability that Z is in good working condition is 5 out of 6. So 5 divided by 6 is 0.8. You can make it 0.8. And then this one is 0.2 there. 0.8 and 0.2. Otherwise, it is 1 out of 10. The one otherwise means everywhere else. 1 out of 10 is 0.1. So this is 0.1 here, and this is 0.9. 0.1, 0.9. 0.1, 0.9. So we are now told the probability that the machine is effective. So machine is effective. Machine is effective. So we have been told that the machine is effective only when Z is in good working condition. So that machine is effective here, or here, or here, or here. So it has 4 possibilities. So if there are 4 possibilities, I will say it is the probability of X working, Y working, and Z working. Then the other one, this one, probability that X is working, Y is not working, but Z is working. This other one, probability that X is not working, Y is working, and Z is working. And this other one, probability that X is not working, Y is not working, and Z is working. So I get these probabilities. This will be 0.7 times 0.6 times 0.8. This other one will be 0.7 times 0.4 times 0.1. This will be 0.3 times 0.3 times 0.1. This other one will be 0.3 times 0.7 times 0.1. So I will need to say 0.7 times 0.6 times 0.8 is 0.336. 0.7 times 0.4 times 0.1 is 0.028. 0.3 times 0.3 times 0.1 is 0.009. 0.3 times 0.7 times 0.1 is 0.021. So if you combine, that is giving me 0.394. Is that fine? Are you fine there?
Yes. I'm following it.
So probability that only one component, Y or Z, is in good working condition. So if you are told probability of only one, only Y or Z working, it means that X has failed, but Y is working, Z is failed, because we just want one, just Y. Or probability that X has failed, Y has also failed, but Z is working. Maybe we are just one. So this becomes 0.3 times Y working here is 0.3, and Z having failed in this one. So we are in this line 0.9 plus 0.3 here, X having failed, followed by Y which has failed, and then Z which is working, 0.7 and 0.1. So if you work out that, you get 0.3 times 0.3 times 0.9 plus 0.3 times 0.7 times 0.1, 0.102. That is the answer. Probability that component Y is in good working condition, given that Z is in good working condition. So that one is straightforward. Where Y is working and Z is working, that is the meaning. Is where Y is working and Z is working. So where both of them are working, it is probability that X is working, Y is working, and Z is working. Or probability that X is not working, Y is working, and Z is working. Because we want where Y is working, given that Z is working. So those two. So if after this one, it will be 0.7 times 0.6 times 0.8 plus 0.3 times 0.3 times 0.1. So 0.7 times 0.6 times 0.8 plus 0.3 times 0.3 times 0.1, 0.345. So I'm thinking that is good enough to understand probability trees. For more, you can refer the book. The book has several others. It will help you get a good understanding. So is that okay, Mohammed?
Yes, yes, Malim.
So then we can call it a lesson at that point.
Thank you so much.
Okay, thank you so much.